Swayam Prabha. Digital India. Educated India.
Hello students, welcome to the class. So today we have an opportunity to discuss about the regioselectivity or the regiochemistry of the Diels-Alder reaction. So in the previous class we have discussed something about the stereochemistry of the Diels-Alder reaction. So we discussed in the name of Cis rule and also the proposed by the Alder, right. So in the Cis rule, the stereochemistry of the Diels depends upon the diene and also the dienophile. So as well as in the endo rule, so the endo rule is based upon the attachment of an unsaturated substituent in conjugation to that of the double bond of a dienophile, right. So most probably according to the endo rule, when the cyclic dienes are involved, so you will be able to see the endo product as the major product. But of course, the reaction also depends upon the reaction conditions like temperature. So if you increase the temperature or prolong the reaction for several hours or several days, so then there is always a possibility of exchange of the isomer, that is exo-isomer predominates over the endo-isomer, right, because we have studied the energy profile for that Alder's endo rule as well. So the endo product is a kinetic product which has always the chance of going back to the reaction reactants and also coming after gaining so much of activation energy, coming again towards the exo product, which is a thermodynamically stable product, right. So regioisomers or the stereoisomers are only possible in the case of Diels-Alder reaction when there are substituents attached to the diene as well as the dienophile. If there are no substituents and there is only a simple diene molecule 1,3-butadiene and there is a simple dienophile, so you cannot expect any stereochemistry in the product cyclic adduct as well as any regiochemistry in the cyclic adduct formed, right. So whenever there are substituents and based on the position of the substituents, you can always expect the regioisomers being formed in the reaction at the end of the Diels-Alder reaction, right. So that means the chosen diene as well as the dienophile should be unsymmetrical, That means there are different substituents at different positions. So you can have a substituent at the C1 carbon atom of the diene, you will get a different set of regioisomers. If you have a substituent at the second position of the diene, you will get a different set of regioisomers. Similarly, if there is a substituent attached to the dienophile, so this gives you the possibility of getting different types of isomers, right. So what does it mean? Means the relative orientation of the diene with a set of substituents and the relative orientation of the dienophile, that also with a substituent, is going to decide the regioisomer, that is the predominating regioisomer. So if you see the regioselectivity or regiochemistry of Diels-Alder reaction. Right. So if you see the simple Diels-Alder reaction between a diene and a dienophile, so there are no such substituents differentiating the positions. So you will be seeing the plain cyclohexane molecule, right, cyclohexene molecule. Whereas if the diene which is involved in the reaction is unsymmetrical, let us say there is a substituent, and at the same time if the dienophile involved is also having a substituent, right. Now the relative orientation of the diene and dienophile, because they are provided with some substituents and they are no more symmetrical, they are unsymmetrical in nature. So, that will give you some regioisomers. So, then only you are able to see some regioisomers formed here, right. So, what kind of isomers you will be seen means based on the position of the substituents and also the relative orientation of the diene and the dienophile, there are possibilities of 1, 2 regioisomer, which is similar to ortho isomer, like orthoisomer, right. You can also have a chance to see 1, 3 regioisomers. So, which is a meta-like isomer. So, and also 1, 4 regioisomer, which is a para-like isomer. So, that means in the cyclic adduct, the relative positions of these two substituents may be either 1, 2 or 1, 3 or 1, 4, which is in common terminology called as like orthoisomer or like a meta-isomer or like a para-isomer. So, that these types of isomers are possible based on the relative orientation of the diene with respect to the dienophile having the substituents, right. So, in the diene case, you can have an option of two positions. So, the first thing is the diene can have a substituent at the C1 carbon atom. So, if this is the C1 carbon atom 2, 3, 4, if the substituent is on the C1 carbon atom, on reaction with a dienophile with some substituent will always give you two different types of regioisomers, that is R and X. So, this is something like an orthoisomer, and it can also give you a meta. So, if the diene is having the substituent at the second carbon atom, C2 carbon atom, let us say this one. So, in the previous case what we have seen is the diene having the substituent at the C1 carbon atom, as a result of which you will get two possibilities, one is the orthoisomer and the other is the meta-like isomer. If the substituent is on the second carbon atom of the diene, so then on reaction with a dienophile, that too having a substituent, you will be allowed to see this is the carbon and this is the substituent at on the dienophile. So, again you will be seeing a meta isomer as well as a para isomer. Right. So, that means whether the position is on the C1 carbon atom or on the C2 carbon atom, you will be seeing three different types of isomers. One is the ortho-like isomer, other is the meta-like isomer, and the last one is the para-like isomer. But as the Diels-Alder reaction is highly regioselective, two isomers will be predominating the reaction. So, what are those two isomers means? Either orthoisomer or the para-isomer will be predominating over the meta-isomer. That means the meta-isomer, the chances of getting the meta-isomer in the Diels-Alder reaction according to the regioselectivity is very minimal. In most of the cases it might be 0 also, right. So, you could only be seeing the orthoisomer or the para-isomer as the predominating products, major products. So, how to explain this property of the Diels-Alder reaction? So, again we need to take some help from the Frontier molecular orbital theory. So, based on the Frontier molecular orbital approach, you can easily understand why these particular regioisomers are being formed. So how means it depends upon the orbital coefficients of the atoms which are participating in the formation of the new sigma bond. So what are the atoms involved in the formation of the new sigma bonds? In the case of diene, it is the C1 and C4 carbon atoms, and in the case of dienophile, it is C1 and C2 carbon atoms, right? So depending upon the orbital coefficients, so greater is the orbital coefficient of a particular atom, greater will be the chances of overlapping with the other atom, and therefore resulting in the formation of a bond, right? So the orbital coefficients developed on the C1 and C4 carbon atom with respect to the type of the substituent on the diene, and the orbital coefficients developed on the C1 and C2 carbon atoms with respect to the substituent attached to the dienophile will tell you the formation of the regioisomers, right? So whether para isomer is forming or the orthoisomer is forming, or in some rare cases meta isomer is forming. So it depends upon the orbital coefficients. Larger orbital coefficients will give to the larger extensive overlap or the bonding or the interaction between the atoms. So interaction will be more if the orbital coefficients are largest at that particular site or atom. Okay. Now, how this can be defined? So in the previous class itself, so we understood that the presence of an electron releasing group on the diene and an electron withdrawing group on the dienophile can accelerate the reaction, increase the rate of reactivity of that particular diene and also dienophile to involve in the Diels-Alder reaction and thereby give you the cyclic adduct molecule, right? So what is happening if there is an electron releasing group on the diene part? So this is the diene part. If an electron releasing group like OMe, methoxy group or something is there on the C1 carbon atom, this is 1, 2, 3 and 4. So what will be happening means this will be pushing the electron density towards the diene, and therefore largest coefficients are observed like this. So negative charges are formed on the C4 carbon atom, right? So when there is an electron releasing group attached to the diene at the C1 carbon atom, the largest orbital coefficient can be seen on the C4 carbon atom, that is the termini of the diene. Okay. If an electron withdrawing substituent is attached to the dienophile, then also this dienophile will be more reactive, right? What is happening here? This is pushing the electron density, pulling the electron density towards the carbonyl group. So therefore, what you will be seeing here is the relative positive charge here and like this. So which can be also written as, so positive charge like this, right? So this can be also written as plus. So while talking about only the things like this. So this is what happening when there is an electron releasing group attached to the diene and an electron withdrawing group attached to the dienophile. So this is what is happening. Now these two are very reactive in nature because of the presence of an electron releasing group on the diene and electron withdrawing group on the dienophile. They too will react, and this becomes the nucleophilic center, nucleophilic in nature, and this is electrophilic in nature. nature, right? So those two can now add with each other, right? So now these two can add with each other, undergoing 4 pi supra plus 2 pi supra cycloaddition reaction, resulting in the formation of a ortho-like isomer, right? So what if the same electron releasing group on the diene is present at the C2 carbon atom instead of the C1 carbon atom? Let us see that. So this is the diene, and now the electron releasing group is on the C2 carbon atom. This is 1, 2, 3 and 4. So now on treating it with an dienophile, activated dienophile like this, so the charge are like this, the electrophilic center is here, and now what is happening here means, so the electron density is shifting to the C1 carbon atom of the diene, right? So therefore you can see this as delta minus. So this is the nucleophilic center of the diene and this is the electrophilic center of the diene. So largest coefficients are seen at the C1 carbon atom of the diene and C1 carbon atom of the dienophile. Therefore, the dienophile has to readjust itself such that the electrophilic center is close to the nucleophilic center of the diene. Now, the Diels-Alder reaction will take place. This is 4 pi plus 2 pi, resulting in the formation of OMe on the second carbon atom of the diene, and then this is here. So what is this? This is a 1,4 isomer, which can also be treated as para-like isomer. So now you got the explanation that why and how the orthoisomer and para-isomer are being produced during the reaction of a substituted diene with a substituted dienophile. That means an unsymmetrical diene and an unsymmetrical dienophile on reaction is going to give you some regioisomers, right? So this is the concept. Now we will see some examples related to the regiochemistry of the Diels-Alder reaction. So this is the diene with a substituent at the second position, and this is a dienophile with an electron withdrawing substituent attached to it. This on Diels-Alder reaction 4 pi plus 2 pi, what you will be seeing? OCH3 and Cn, right? So you will be seeing the para-like isomer. If the substituent is on the first position, first carbon atom, so this is the dienophile. On reaction, so what you will be seeing? Of course, you will be getting an endoisomer, OMe, Me, hydrogen, right? So this is below the plane. At the same time, this is also below the plane. So, you will be getting an endoisomer, and at the same time the regiochemistry is this way, right? Why? Because the electron releasing substituent is on the first carbon atom, therefore nucleophilic carbon atom is the fourth carbon atom. Here this will be little positive. So, therefore, they will react such a way that it gives you the ortho-like isomer. Now, this is an interesting example. If you see this, this is a diene with a heteroatom, right? And now, if you make it to react with some dienophile like this, okay. So, what is happening means you will get definitely some product like this, you will be getting a product. But if you closely observe this reaction, in the previous class something we have also discussed. The Diels-Alder reactions are classified as normal electron demand Diels-Alder reaction and inverse electron demand Diels-Alder reaction. So, what is inverse electron demand Diels-Alder reaction means? When there is an electron releasing group attached to the dienophile and some electron withdrawing group attached to the diene, so then the roles becomes different, right? So, usually the dienophile should be nucleophilic, diene should be nucleophilic and the dienophile should be electrophilic in nature, right? So, but what is happening here means there is a carbonyl group and which creates the positive charge over here, and there is a methoxy group which generates negative charge over here, right? So, the charges have been changed here. So, therefore, this is electron rich dienophile. This is a dienophile of course, but electron rich in nature. This acts as a diene, but of course electron deficient diene. So, if the diene is electron deficient and at the same time if the dienophile is electron rich, so the reaction happening here is called as inverse electron demand Diels-Alder reaction. Inverse electron demand Diels-Alder reaction. So, while looking at the diene and the dienophile, many things you need to keep in mind, that is the nature of the substituent, the position of the substituent, and how stereoisomers what you will be able to get and the regioisomers what you will be able to get, right. So, this is the thing. Now, look at this example. So, there is an electron releasing group at the second position of the diene and the dienophile is having two such electron withdrawing groups here, right. Both of them are electron withdrawing in nature. Now, so now if you compare these two electron withdrawing groups, nitro group will win the race, and therefore what you will be seeing here is a cyclic adduct molecule COO CH3 and then this nitro group will predominate. So, nitro group is predominating the ester group, and one more thing you need to observe here carefully is that the dienophile which you have taken is a trans stereochemistry, is having the trans geometry. Now, in the product also it retains that same thing, it is still trans in nature according to the cis rule. So, in the previous class we have discussed about this, right. So, next topic is the Lewis acid catalyzed Diels-Alder reaction. So, we have had some idea what the Lewis acid as a catalyst is going to do with the Diels-Alder reaction. So, any catalyst, if it is a positive catalyst, will accelerate the rate of reaction and gives you the more yield. right? Any catalyst which is a retardant will deaccelerate the reaction and decreases the rate of reactivity. And in the Diels-Alder case, some Lewis acids are capable of acting as the catalysts, They will accelerate the rate of reaction. That's for sure we know. In this Diels-Alder reaction, when you are dealing with the unsymmetrical diene and dienophile, these Lewis acid catalysts will further activate the dienophile, not only accelerating the rate of reaction, but also will decide the regioisomer, That means which regioisomer should predominate is also decided by the Lewis acid catalyst. So, there are certain Lewis acid catalysts like AlCl3, BF3, SnCl4, etc. They will act as Lewis acid catalysts. So, besides being as catalysts, increasing the rate of reaction, they also increase the regioisomer. Let us see this example. So, this is a 2 substituted diene, right? At the second position, you have an electron releasing group, and upon reaction with a dienophile, like this, you are able to see 2 different isomers, right? This is the para isomer, and you can also see this meta isomer. So, this reaction is going to give you 2 different types of isomers, is what we can see basically here, right. So, when is this happening? Under means in a sealed tube, the reaction proceeds in a sealed tube at 120 degrees centigrade. So, if you perform this reaction in a sealed tube at 120 degrees centigrade without any Lewis catalyst, so you will be able to see 71% of this para isomer and 29% of this isomer. Whereas, the same reaction in the sealed tube, if you use SnCl4 as the catalyst, SnCl4 5H2O as the catalyst. At 0 degree centigrade also, the reaction will happen. So, previously you have to heat this at 120 degree centigrade in a sealed tube, but now in the presence of a Lewis acid catalyst at 0 degree centigrade itself the reaction is possible, and what you will be able to see the difference in the isomers is 93% of this para isomer and only 7% of this meta isomer is going to be seen in the presence of the catalyst, right. So, another example is with cyclopentadiene on reaction with acrylic acid. So, obviously, when you use cyclic dienes, then Alder's endo rule has to be also considered. So, a cyclic diene on reaction with a dienophile which is connected to an electron withdrawing unsaturated group. So, this is an unsaturated system functional group, so which is in conjugation with the dienophile, right. So, then according to the Alder's endo rule, so you will be seeing 2 different types of isomers, endoisomer as well as the exoisomer, and endoisomer will predominate plus right. So, the reaction happens at 0 degree centigrade itself, and the catalyst will change the ratio of the isomers. So, with no catalyst at 0 degree centigrade, what you will be seeing here is 84% of endoisomer to 16% of exoisomer. So, when there is no catalyst, you will be able to see 84% of the endoisomer and 16% of the exoisomer only. In the presence of a catalyst like AlCl3 at 0 degree centigrade itself, what the change you can observe here is 93% of the endoisomer and only 7% of the exoisomer. So, the percentage of endoisomer has increased from 84 to 93% in the presence of a Lewis acid catalyst, right. So, why this is happening means, again take the help of frontier molecular orbital theory. So, when there is a functional group attached to the dinophile, upon treating it with a Lewis acid catalyst like AlCl3 or BF3 etc., what happens is reversible coordination takes place with the Lewis acid catalyst, right. So, AlCl3 coordinates with the functional group of the dinophile. Itself is an activating group, it is activating the dinophile. Upon that, if it is attached or coordinated to a Lewis acid, means the more will be the electron density pulled out from the dinophile. That means more will be the positive charge developed on the dinophile. The more the electron deficiency on the dinophile and more the electron sufficiency or electron rich character on the diene will obviously drive the reaction towards the forward direction, right. So, that means the rate of reaction increases. So, this is the case. So, how we can see that means in this particular reaction itself, so if there is a diene on reaction with a dinophile, right. So, the diene has Psi1, Psi2, Psi3 and Psi4. So, Psi1 is having 2 electrons and Psi2 is also having 2 electrons, and this is regarded as the homomolecular orbital. So, Psi3 and Psi4 are there. In the case of dinophile, you have Psi1 and you have Psi2, which is a lumomolecular orbital. If you see the difference between the HOMO and LUMO, this is the case in the absence of catalyst. So, when we are talking this in the absence of catalyst. In the absence of Lewis acid catalyst. So, this is the energy gap between the HOMO of the diene and LUMO of the dinophile. The same reaction if you perform in the presence of a Lewis acid catalyst. So, this is the Psi1, Psi2, Psi3 and Psi4 of the diene, and this is the Psi1 of the dinophile and Psi2 of the dinophile. So, the Psi2 of the diene acts as the homomolecular orbital, Psi2 of the dinophile will act as the lumomolecular orbital. Now, you see this, there is no change in the energy of the molecular orbitals of diene. So, this is the energy axis, right. This is the energy axis. In the presence of catalyst, what you have observed here is the distance of separation between the HOMO and LUMO has drastically decreased. That means the lumomolecular orbital of the dinophile is extensively stabilized by the Lewis acid catalyst. The lumomolecular orbital of the dinophile is stabilized by the Lewis acid catalyst. So, therefore, the energy gap between HOMO of the diene and LUMO of the dinophile has reduced. So, which promotes the reaction very easily. So, this is the frontier molecular orbital approach towards the explanation of catalyst activity or catalyst being catalyzing or activating the dienophile, right? So, this is all about the regioselectivity or the regiochemistry of the Diels-Alder reaction. So, in the next class, we will see about 1,3 dipolar cycloaddition reactions involving 1,3 dipolar cycloaddition reactions and also some higher order cycloaddition reactions. Thank you.